Section 6.7 Many Electron Atoms. One of our goals in this chapter has been to determine the electron structures of atoms. So far, we've seen that quantum mechanics leads to a very elegant description of the hydrogen atom. This atom, however, is only one electron. How must our description of the electronic structure of atoms change when we consider atoms with two or more electrons? To describe these atoms, we must consider the nature of orbitals and their relative energies, as well as the electron populate the available orbitals. Section 1. Orbitals and their energies. The quantum mechanical model would not be very useful if we could not extend what we have learned about hydrogen to other atoms. Fortunately, we can describe the electronic structure of a many-electron atom in terms of orbitals like those in the hydrogen atom. Thus, we can continue to designate orbitals as 1s, 2p to the x, and so forth. Further, these orbitals have the same general shapes as the corresponding hydrogen orbitals. Although the shapes of the orbitals of many electron atoms are the same as those for hydrogen, the presence of more than one electron greatly changes the energies of the orbitals. In hydrogen, the energy of the orbital depends only on its principal quantum number, n. The 3s, 3p, 3d subshells all have the same energy. For instance, in a many-electron atom, however, the electron-electron repulsions cause the different subshells to be at different energies, as shown in Figure 625. Figure 625, Orbital Energy Levels in Many-Electron Atoms. In a many-electron atom, the energies of the subshells in each shell follow the order of in the S, in P, in D, in F, as in Figure 18, each box represents an orbital. To understand why this is so, we must consider the forces between the electrons and how these forces are affected by the shapes of the orbitals. We will, however, forego this analysis until Chapter 7. The important idea is this. In a many-electron atom, for any given value of n, the energy of an orbital increases with increasing value of L. You see this illustrated in Figure 625. Notice, for example, that in the n equals 3 orbitals, increase in order of 3 is less than 3p is less than 3d. Figure 625 is a qualitative energy level diagram. The exact energies of the orbitals and their spacings differ from one atom to another. Notice that all orbitals of a given subshell, such as the 5 3d orbitals, still have the same energy as one another, just as they do in the hydrogen atom. Orbitals with the same energy are said to be degenerate. Section 2. Electron spin and the Pauli exclusion principle. We have now seen that we can use hydrogen-like orbitals to describe many electron atoms. What, however, determines which orbitals the electrons reside in? That is, how do the electrons of a many-electron atom populate the available orbitals? To answer this question, we must consider an additional property of the electron. When scientists studied the line spectra of many-electron atoms in great detail, they noticed a very puzzling feature. Lines that were originally thought to be single were actually closely spaced pairs. This means, in essence, that there were twice as many energy levels as there were supposed to be. In 1925, the Dutch physicists George Uhlenbeck and Samuel Goudsmit proposed a solution to this dilemma. They postulated the electrons have an intrinsic property called electronic spin that causes each electron to behave as if it were a tiny sphere spinning on its own axis. By now, it probably doesn't surprise you to learn that electron spin is quantized. This observation led to the assignment of a new quantum number for this electron in addition to the n, l, and m1, which we've already discussed. This new quantum number, called the spin magnetic quantum number, is denoted by m sub s. The subscript stands for spin. Two possible values are allowed for m sub s, positive 1/2 and negative 1/2, which was first interpreted as indicating the two opposite directions in which the electron can spin. A spinning charge produces a magnetic field. The two opposite directions of spin therefore produce oppositely directed magnetic fields, as shown in Figure 626. Figure 626, Electron spin. The electron behaves as if it were spinning about an axis. thereby generating a magnetic field whose direction depends upon the direction of spin. The two directions for the magnetic field correspond to the two possible values for the spin quantum number m sub s. These two opposite magnetic fields lead to the splitting the spectral lines into closely spaced pairs. Electron spin is crucial for understanding the electronic structures of atoms. In 1925, the Austrian-born physicist Wolfgang Pauli discovered the principle that governs the arrangements of electrons in many electron atoms. The Pauli exclusion principle states that no two electrons in an atom can have the same set of four quantum numbers, n, l, m1, and ms. For a given orbital, 1s, 2pz, and so forth, the values of n, l, and m1 are fixed. Thus, if we want to put more than one electron in an orbital and satisfy the Pauli exclusion principle, our only choice is to assign different m sub s values to the electrons. Because there are only two such values, we conclude that an orbital can hold a maximum of 2 electrons and that they must have opposite spins. This restriction allows us to index the electrons in an atom, giving their quantum numbers and thereby defining the region of space where each electron is most likely to be found. It also provides a key to one of the great problems in chemistry, understanding the structure of the periodic table of elements. We'll discuss these issues in the next two sections.